I will share my slide now.
Yeah.
Can you see them?
Yeah.
Okay, thank you. Hi everyone, my name is Alice Tarzariol and I'm a PhD student at the University of Klagenfurt under the supervision of Professors Martin Gebser and Konstantin Schekotihin. Today I will talk about our work titled Lifting Symmetry Breaking Constraint with Inductive Logic Programming, which extends a work that we presented at IJCLR this year. So symmetries in combinatorial problems are widely studied, and if we remove them, we avert useless computation. In our work, we deals with the answer set programming paradigm, and we consider asymmetries as a set of truth atom assignments. Ideally, the programmer should model the problem such that the symmetric solution do not appear. Nevertheless, if this happens, we can still use automatic procedure that can identify and discard asymmetries. Such procedures are called instance-specific approaches, and they can automatically identify and remove the symmetries according to syntactic properties of the current instance. In general, they perform the following steps. So they first define a reduction of the current problem instance into an instance of the graph automorphism problem. Then they use efficient tools to find symmetric vertex permutation of such graph, and then reduce them into symmetries of the original problem. At this point, they add symmetry breaking constraints to remove the symmetries according to a certain criterion. And one of the most popular one is the lexicographic leader, which can guarantee that at least the minimal object among the symmetric one is preserved. So for ground ASP programs, we have the systems bus, which performs this approach. And although it aims to speed up the solving of the ground instance, we can identify the following limitations, especially if we consider a set of instances which follow a distribution. So the approach is, as I said, instance specific, which means that the constraints learned are ground and cannot generalize as first order constraints. Moreover, they are often hard to interpret and comprehend because they're not represented in their symbolic representations. And we have generally a huge amount of them. Then we have to consider that every time that we use bus, we have to perform a pre-computation phase where we identify the symmetries, and this can burden the solving procedure itself. And last but not least, it could be that for some combinatorial problems, we have many redundant ground constraints, and they lead to more drawbacks than benefits for the solver. So for this reason, we suggest a framework that can compute the symmetry breaking constraints offline for a set of small but representative instances, and then lift them using inductive logic programming. So very quickly, the framework that we suggest has 5 inputs that have to be defined. We have the ASP program P. We have 2 sets of instances, S and Gen, which contain satisfiable, representative, and small instances for P. We have another ASP program, ABK, which contains auxiliary predicate to consider, and where we will append the constraint that we learned so far. And lastly, we have also to define the search space. So before solving the ILP task, we have to define the examples, and we do that by exploiting the 2 sets of instances. So for each instance in Gen, we define a general positive example. So with this, I mean that the positive example for each of those instances guarantee that the learned constraints have to preserve at least a solution of each of such instances. Then for each instance in S, we use SBUS to analyze the symmetric solution, so the symmetric and non-symmetric answer sets, and we label them as positive or negative example according to the approach that we define. Actually, we define 4 approaches to do so, and in the next slides, I will briefly define them. So then at this point, we have all the items to define an ILP task, and we use the ILP system ILASP, which works for ASP paradigm, and it learns first order constraints that will be appended to ABK in order to use this framework incrementally and learn new constraints. So the 4 approaches that we define are the following. Very briefly, we have enum, which enumerates all the answer set obtainable for each single instance in S, and use the lexicographic leader criterion over the symmetry identified with SBUS to label the answer set as either positive or negative examples. Similarly to enum, we have another approach, SAT, that instead of defining a set of positive examples, it defines a single positive example per instance, similarly to how we define the example for the instance in Gen. So now the meaning is that we learn constraints that preserve at least a solution also for those instances. Then we implement an alternative atom ordering for the lexicographic schema with the aim to learn shorter first order constraints for configuration problem encodings. And lastly, we define the approach full, which labels the answer sets as positive or negative example according to full symmetry breaking rather than partial. And we do so by exploring the orbit of symmetric interpretation. So here we can see the implementation of our framework, especially the highlighted part concern the creation of a set of examples from each instance in S with the approach enum. So as you can see, we start by grounding the inputs, and in parallel, we launch SBUS to identify the symmetries, and we enumerate all the answer set of the instance. Then we use the lexicographic leader criterion to distinguish whether an answer set is dominated or undominated. And we use this information to define a positive or negative examples. We do this procedure for all the instances in S, and we union all the examples and consider also the general examples produced from the set Gen. The search space is defined from a set of mode declaration for the first order constraints, which contains the predicates in the program P and ABK. As I said, ABK contains auxiliary predicates that we define for allowing the usage of comparison and arithmetical operations in the learned constraints, which are not provided by default by ILASP. And then we, for reducing the learning time, we run ILASP incrementally by gradually extending the language bias. So we test our framework over 3 versions of the pigeonhole problems and the house configuration problem. Here I will show you just the results that we obtain with the last problem. So house configuration problem belongs to the family of rack configuration problems, and it consists of assigning T things of P person to C cabinets, where each cabinet has a capacity limit of 2 things that must belong to the same owner. In the table, you can see with the white rows, the unsatisfiable instances, and in gray, the satisfiable ones. So the first things that I would like to show you is the performance that we obtain for with a basic modeling that doesn't deal with the symmetries. And here you can notice that the worst performance are obtained when the instances are unsatisfiable because of the symmetries, reaching the timeouts of 900 seconds. On the other hand, with the pre-computations of the symmetries with SBUS and the solving of the extended program with the ground symmetry breaking constraints, we can notice two scenarios. So the first scenario is when the instance is too big, and this is the case for instance, for the satisfiable instances, and the pre-computation of the symmetries already reached the timeout without even having the time to solve the augmented instance. On the other hand, when SBUS managed to identify the symmetries, what can occur can be seen in the highlighted row. We can notice a degradations of the performance of the ground symmetry breaking constraints because of their redundancy. So in the highlighted rows, we see that the time needed to solve the extended programs is higher than the original one that doesn't handle the symmetries. So on the other hand, the performance that we obtain with the program extended with the first order constraint, the best first order constraint that we found with our 4 approaches, managed to improve the performance for both satisfiable and unsatisfiable instances. Especially for this example, we notice a huge improvement for the with the approach full, especially for the unsatisfiable instances. So to conclude, I will briefly sum up. We have seen that the limitation of instance-specific symmetry breaking constraint approaches like SBUS can be overcome by a careful selection of representative set of instances and the application of ILP, in our case, ILASP, to learn first order constraints. So far, we addressed just simple combinatorial problems with some characteristics, but in the future, we would like to tackle some more advanced configuration problem, like, for instance, the parted unit problems or graceful graph labeling. To do so, we need to address the scalability issues that may occur. So we have to avoid the analysis of all the answer set for the analyzed instances with the instance that we analyze with SBUS. And we have to consider, we might consider alternative predicates in ABK that are more efficient for the grounding and solving. And lastly, we would like to evaluate and automate the generation of the inputs of our framework, which right now are defined manually, so that the learned constraints evolve incrementally. That was it. Thank you very much for your attention. If you have any question, I will be happy to answer them.